Okay, so we're going to start looking at the homework assignment for module number 3. So we've really kind of hit elements of all the different types of problems that you have. So now it's a good time to kind of jump in and start looking at the homework assignment. Now, there are quite a few problems here. I agree, but let's look at them individually. And I think you'll see that, you know, they're not all as involved as especially the last problems that we did. Okay, so so on page 161 is where the homework assignment starts. So I'm going to go underneath my camera here. And you'll notice that the first problems that we have are 1 through 6. Okay, so number 1, 2, 3, 4, 5, and 6. Now, each one of these, this is just looking at general velocity. The intent here is to, you know, get us familiar again with the velocity stuff. And this would have been like covered in part in our first lecture that we did the last time we were together. Okay, so looking first at 6.1, it says here a package is moved at a constant rate from one end of a 25-foot horizontal conveyor to the other in 15 seconds. Determine the linear speed of that conveyor belt. This was actually just like one of the example problems that we did in the very beginning of this chapter. If we look back, it will be example 6.1 is exactly the problem 6.1 that I'm asking you to do. So this is what you would want to mimic when you do that problem. And it's just taking the distance of the conveyor divided by the time it takes to you know, go that distance, and then that's going to be your velocity in single unit increments. Okay, so that's number 1. The next one that we have here, a hydraulic cylinder extends at a rate of 2 feet per minute. Determine the time required to traverse the entire stroke of 15 inches. Okay, of 15 inches. So determine the time. So you would want to know, probably not in minutes, probably in seconds, how long it would take if you're going 2 feet per minute, how long would it take to go 15 inches in seconds? Okay. The cylinder is an entire stroke of 15, so it would be just in one direction. So just like from 0 to 15, that would be the total stroke. Yeah. So how long does it take something that's going at 2 feet per minute to go 15 inches? All right. The next one, it says, determine the average speed in miles per hour of an athlete who can run a 4-minute mile. So it takes them 4 minutes to run 1 mile. Okay. So we would say 1 mile divided by 4 minutes, but now it's basically a conversion to miles per hour then. How many miles per hour, if they would go at that same rate, how many miles could they cover in 60 minutes? Okay. Number 4, determine the average speed in miles. I'm sorry, in miles per hour for an athlete who can run the 100-meter dash in 10 seconds. So here again, it would be 100 meters per 10 seconds, top bottom, and now you would just convert that to miles per hour. Okay, so conversion for those. The next one here, number 6.5, a gear uniformly rotates at 270 degrees clockwise in 2 seconds. Determine that angular velocity first in revolutions per minute. So it's just a conversion from 270 degrees to revolutions per minute, or 270 degrees in 2 seconds to revolutions per minute, and then converting the revolutions per minute to radians per second. And then number 6, determine the angular velocity, that's W in RPM, of the second, the minute, and the hour hand on a clock. So that's 3 of them that you have to do. What is the angular velocity of the second hand? What is the angular velocity of the minute hand? And what is the angular velocity of the hour hand on a clock? Okay. So any questions at the moment on each one of those? You might not know exactly how to do it, but for primarily, most of them are conversions. Yeah, no diagrams to do. So the next problem that you have is going to be number 11. All right, number 11, the statement is at the bottom of that first column, but we're going to be looking at the diagram in the second column. So it says we have a drive roller on a conveyor belt is shown. Determine the angular velocity of the roller when the belt operates at 10 feet per minute. Okay, so if we look here, here is our conveyor. Oopsie. And the belt is going along in this orientation. And we want to know, what is the velocity of that belt? Like how many, feet per minute, or actually the belt is going at 10 feet per minute. Okay, that's its velocity, 10 feet per minute. Okay. And we want to know how fast is this going around in RPMs. All right. So if we relate this to what we've been looking at, if this is a link, for instance, a rigid link going straight up, and this point would be point B, and point B would be going at a velocity of 10 feet per minute, what would the angular velocity of that link, that roller, actually be? Do you kind of see how that's related to what we were doing earlier? Okay. So I'll kind of leave it there. W is equal to V over R. You know what your straight line velocity is. You know the distance or the radius of that roller. So you can calculate W, but you've got to use the right, units so that you can get it into revolutions per minute. Okay, because that's what you're going to have for the roller. Revolutions per minute is going to be the final number here. Any questions on that one? Okay. So here as well, the drive roller of the conveyor belt is shown in that figure. Determine the linear speed of the belt when the roller operates at 30 RPM counterclockwise. Okay, so now they're giving you the speed of the roller. So it's going to be going in a counterclockwise direction, same as what's seen here at 30 RPM. And now they want to know what's the velocity then of that belt. So kind of going in the opposite direction. For this one then, your V is going to be equal to WR. Okay. Any questions there? All right. The next problem, we're going to turn the page. The next problem is at the top of the second column on page 162. Here we have 619. It says for the compressor linkage that we see, use the relative velocity method to graphically determine the linear velocity of the piston as the crank rotates clockwise. Okay, so clockwise is this way at 1150 RPM. Okay, this is just like the last problem that we did in our handout. Okay, but different numbers, right? So that's 19. 21. For the reciprocating saw shown down here, use the relative velocity method to graphically determine the linear velocity of the blade, which is the slider again, okay? As the crank wheel is going to go around counterclockwise, so this way, counterclockwise, at 1500 RPMs. All right, so that's going to be a crank slider or a slider crank mechanism again, like that last problem we did in the handout. The next one is number 23. These three look familiar, don't they? You might be able to go back and see your original kinematic diagrams and see if they match. I'm not sure if they do definitively, but the arrangement will be the same, even if you have to do any, tweaking of the dimensions. So here for the shearing mechanism, use the relative velocity method to graphically determine the linear velocity of the blade as that crank is going to rotate clockwise at 100 RPMs. Okay. So what's going on up and down here and in what direction? That's number 23. Number 27 is over on this side. It's right here. We have a sloshing bath used to wash vegetable produce. For the configuration shown, use the relative velocity method to graphically determine the angular velocity of the water bath, or I'm sorry, of the water bath as the crank over here is driven counterclockwise at 100 RPMs. So here's the bath, it's going to oscillate. And then here is the crank that's going to be going around. Okay, so this is going to be like the first problems, like a crank rocker type of a problem. And you want to know what the angular velocity is of the water bath. So that's going to be a W4 for this one. And then number 28, the device up here, slashing bath is used for the configuration shown, goes to the top of the next column. Relative velocity to graphically determine the angular velocity of the bath as the crank now is driven clockwise rather than counterclockwise at 75 RPMs. So this time we're now going to be going in this direction. So same problem, just a little bit different numbers again and direction changes. So you have two of those to do with the same original diagram. And then the last two problems that you have are going to be numbers 31 and 32 related to this shear, which I think also it looks like a familiar mechanism for us. So in this one, we want to graphically determine the angular velocity of the handle required to have the blade cut through the metal at a rate of 3 meters per second. So that means it's going to be going down at 3 meters per second. So you'll know the final velocity of the blade this time vertically down. And they want to know what is the angular velocity then of our handle coming back. So that's actually in a different direction than what we've been doing them in. Rather than starting at the crank, if you would, they're starting at what is the end result of the motion that we want. So what do we have to do over here? Okay. And then also determine the linear velocity of point X. That's a link. That's a point on a floating link. So we'll talk about that as well. That's one little subject that we just need to cover yet, but I'll do it when we maybe do an overview of this in a separate video. Okay. And then number 32, in this case, it says, for the hand operated shear, use the relative velocity method to determine the linear velocity of the blade as that handle rotates at, oh, look at how nice they are, 2 radians per second clockwise. Nobody talks like that, but that way you don't have to do the conversion, which is nice. And then also determine that linear velocity of point X, a point on a floating link. Again, we do need to cover that little bit yet, but it's just one little extra step that I'll talk about when we maybe look at this problem, when we do look at this problem, I promise. So kind of as you're looking at the assignment between now and the next time we're together, what I want you to do is just kind of work independently. I'll be available to answer questions so that as things come up, you can get those answered, and then we'll continue starting the next time that we're together. Take any questions, and I presume they're going to be probably on the order of the diagrams that we have here for the relative velocities problems that we have starting with 19, that we'll want to do a couple of these to make sure that you've got a good handle on the process. Okay. All right. So that's an overview of your homework for chapter 6 or module number 3. All right. So I'm going to stop recording.